Welcome to the Phase Transitions Part 2 screencast. The objectives of this screencast are to describe the relationship between vapor pressure, temperature, and enthalpy of vaporization, and to solve problems using the Clausius-Clapeyron equation. In the previous screencast, we looked at what vapor pressure is and the general shape of a pressure versus temperature vapor pressure curve. Now we're going to look at this in more detail, going to deal with it mathematically, and we're going to look at the vapor pressure of water between 0 degrees Celsius and 100 degrees Celsius, and the vapor pressure values every 10 degrees are listed here. And if we graph that, we get a graph that looks like this. This is the shape that we saw before. It's exponential looking, and this is the very specific data for water, its vapor pressure as a function of temperature. Now, an interesting thing happens if we take our data and convert our temperatures to Kelvin and then take 1 over the temperature and take our vapor pressure values and then take the natural log ln of those values. And so we now have new columns of data, 1 over temperature in Kelvin and natural log of vapor pressure. And if we graph that, notice that the graph is linear. This is a very common technique used in science to analyze data, manipulate your variables, and see if you can get the relationship where you get a straight line graph. And in this case, if we look at 1 over t as being our x value and ln of p as being our y value, then we have a straight line where y corresponds to ln of p, x corresponds to 1 over t. It turns out that the slope of this line, the m, is negative delta H of vaporization, so the enthalpy of vaporization, divided by R, the gas constant. And then that happens to equal, but it's offset by a constant. So this should be a familiar straight line formula, slope-intercept y equals mx plus b, where ln of p is our y value, 1 over t, and t has to be in Kelvin here, is our x value. The slope of the line is negative delta H vaporization over R, and when we graph ln of p versus 1 over t, we get a straight line with slope, negative delta H vaporization over R. So this is the linear form of that equation, or the relationship between pressure and temperature. It turns out that this is an equation that can also be derived from theory. It's called the Clausius-Clapeyron equation, and it shows that the natural log of the vapor pressure and 1 over the temperature in Kelvin are directly proportional to each other. It's a linear relationship, and the proportionality constant is negative delta H vaporization over R. So a couple things to note about this. One is, if we take 1 over the temperature in Kelvin versus the vapor pressure for a given substance, if we do that graph, we'll get a straight line, and the straight line will have a slope that's directly related to the enthalpy change or enthalpy of vaporization for that substance. Now, there's another thing we can do, and here's our equation or relationship in this linear form in general. And of course, there's a whole bunch of points on the vapor pressure curve. So if we look specifically at one point, so a very specific temperature, we'll call it temperature 1, and the vapor pressure at that temperature, we'll call it pressure 1. We have this relationship. It holds at any point on the line. Therefore, it's going to hold at a different point on the line. So at temperature 2, which has vapor pressure 2, this equation also holds. And the interesting thing we can do with this is, if we call the top equation equation 2 because it's data point T2 and P2, and we call the bottom equation equation 1 because it's data point P1 and T1, since these are two equations, we can manipulate the equations in specific ways and still have an equation. So one thing we could do is subtract equation 1 from equation 2. And if we do that, on the left side, we have ln of P2 minus ln of P1. And on the right side, we have negative delta H of vaporization over R times 1 over T2 minus negative delta H vaporization over R times 1 over T1. And of course, we'll have the constant C minus the constant C, so that'll cancel out. So putting that all together, we have ln of P2 minus ln of P1 equals negative delta H vaporization over R times 1 over T2 minus negative delta H vaporization over R times 1 over T1. And this is kind of a cumbersome looking equation. We can make it a little bit better by rearranging using laws of logarithms and doing a little bit of factoring out. And so ln of P2 minus ln of P1 is the same as ln of the quotient P2 over P1. We factor out negative delta H vaporization over R, and then that is times 1 over T2 from here minus 1 over T1 from there. So this is a rearranged version of the Clausius-Clapeyron equation. And notice what this then allows us to do. We could graph pressure versus temperature and from the slope get delta H vaporization, but also if we know the delta H vaporization and two temperatures and a pressure, we can get the pressure at another at the other temperature, etc. If we know all but one of the variables in this equation, we can figure out the missing one. So let's try this with an example that's hopefully reasonably straightforward. Here we have some data for benzene. It has a normal boiling point of 80.1 degrees Celsius, and at 60.6 degrees Celsius, its vapor pressure is 400 millimeters of mercury, and we are supposed to find the enthalpy of vaporization for benzene. Well, we know a relationship, this one, that gives us a relationship between temperature, pressure, vapor pressure, and delta H of vaporization. And to get delta H of vaporization, we need two different temperature, pressure, vapor pressure points. And it may not quite look like we have two data points here, but we do if we remember what normal boiling point means. For a substance to boil, it has to have its vapor pressure equal the external pressure, and under normal conditions, the external pressure is 1 atm. So at 80.1 degrees Celsius, the vapor pressure of benzene is 1 atmosphere. Now, of course, we have to have the temperature in in Kelvin, so 353.3 Kelvin, and that corresponds to 1 atm or 760 millimeters of mercury. The other data point is given explicitly at 60.6 degrees Celsius, which is 333.8 Kelvin. Vapor pressure is 400 millimeters of mercury. Note, we have to have the temperature in Kelvin. This equation is only true if the temperature is in Kelvin, but we can have the vapor pressure in different units so long as the two agree with each other. So we could use atm or millimeters of mercury, but we have to be consistent. So we can now set up our equation and plug in the values. P1 is 760 millimeters of mercury. P2 is 400 millimeters of mercury. Temperature 2 is 333.8 Kelvin. Temperature 1 is 353.3 Kelvin. R, the gas constant, is 8.3145 joules per mole Kelvin. And then we know everything in this equation except delta H of vaporization. So it's a pretty straightforward matter. Solve for delta H of vaporization. So we have to take the natural log of this ratio, multiply both sides of this equation by negative R value, 8.3145, to get rid of that. And then this 1 over temperature difference, 1 over T2 minus 1 over T1, we need to get that value and then divide both sides by that. So simple, isolate the variable, usual thing to do. And if we solve, we get delta H of vaporization is 30,300 joules per mole, rounded off to 3 sig figs. And this is a big enough number, and that's typically the case for delta H of vaporization, that by convention, we probably make it into kilojoules per mole or 30.3 kilojoules per mole. Now, of course, we could solve a problem to determine a vapor pressure at a particular temperature if we knew the vapor pressure at a temperature that is different than the one we're trying to solve for, and if we know delta H of vaporization, or any permutation here where we know all but one of the variables. And that is it for the Phase Transitions Part 2 screencast.